All right, so guys, here we are. We're talking about transformers. Transformers are needed to increase or decrease in AC voltage. These only work for AC. They do not work for direct current. The transformer was the main reason that Tesla and Edison were winning in the current wars. Now, a transformer, two coils of wire known as the primary and secondary coil. So you'll notice that there's a laminated core, and I have a mock-up of this, a laminated core that allows for an intensified magnetic field. You know that there's a magnetic field going around the turns of those wires. Faraday's law, actually not Faraday's law, but just the idea that there's a magnetic field around a coil of wire. We know that there's an intense magnetic field in the primary side, and there's an intense magnetic field in the secondary side. The primary is the input side, the secondary is the output side. So it's just terms that we would use to describe which side is the input power coming in, which side is the output. The laminated iron core around which are wrapped the coils they're either interwoven or they're set up like this. When an AC voltage is applied to the primary, the changing magnetic field it produces will induce an AC voltage in the secondary coil. I'm going to draw some graphs up here to make sure we understand where that inducing comes from. It has to be alternating. So on this side, if this is the input side, we know we have an alternating current. So alternating current has to have a positive and a negative. Now, remember, there's two sides for this. So we have a waveform that's coming in and coming out, and we can think of that as alternating. So when I'm in the positive region of this, so this particular portion, when I'm in that portion, I have a north and a south portion around that coil. When I flip into the negative region, what happens to the magnetic field around that coil?
Does it invert?
It changes, right? So now it becomes south and north. Now I know you guys can't do color coding on there, but that's the essence of an alternating current, is it produces a variable magnetic field within that iron core. Now that iron core allows me to have a north-south portion here, but that's the same north-south portion over here, right? Because magnetism is going to be existing throughout that entire thing. Now what I have is a variable magnetic field within the presence of a coil of wire. That generator showed you that when you had a varying magnetic field, what happened in that wire? It induced a current. So what I'm able to do then is transfer the input power to the output power through what's called mutual induction. I am creating a magnetic field on this side that's varying because of the alternating current. That varying magnetic field induces current on the right-hand side. Now what's cool about this is that the output voltage has the exact same frequency as the input voltage. If I'm running this transformer with US power, I probably have 120 volt, 60 hertz signal. That's standard for the United States. That means that the output voltage will be at 60 hertz. But the value of his output voltage depends on the number of loops in each coil. So if I change the number of loops that I have on the secondary and primary, I can either ramp up that voltage or I can ramp it down. So we call them step up or step down. Can you take a look at a moment here? Do you see that I have more turns on the output side than I do on the input side? What I would be doing there is I would be stepping up that voltage through that transformer. Now, the actual amount that it goes up is based on this equation. It's called the transformer equation. It's really simple. It's just a ratio. The ratio of the secondary voltage to the primary voltage is in the same ratio as the number of turns. Let's say, as a numerical example, that the primary side has 100 turns. We would say N on the primary is 100. So I wrap this thing up and I put 100 turns around the primary side. And the secondary side, NS, has 5,000 turns. All I do is just wrap it around more times. The ratio of the input to the output, what is that? Is that 50? Is that 50 times as many turns? Just take the ratio. if I put in 120 volts here, the voltage over there would be, gosh, I should have done this with easier numbers, 50 times
6,000.
I could take that voltage and bring it up to 6,000 volts through that transformer. The value of that has to do with sending energy great distances at different voltages. And so I'll show you, this is why it is that Westinghouse and Tesla sort of won that battle. So we can pump the voltage up, or we can step it up, or we can step it down based on the ratio of those turns. I want to do a couple of examples with you.
That's great.
Okay. Oh, I wanted to show you a picture of this, or a visual of this before we move into this. So when I made this a number of years ago, just as a potential lab, I'm like, oh, I'm going to have kids maybe make this themselves. I didn't end up working really well, so I'm just going to show it as a demonstration. These are just I made this thing completely from materials I buy from Home Depot. Right, and so that's the idea, is that you can just make a simple transformer with materials that you'd find just at your common hardware store. These are L brackets. That's the iron laminated core. The outside of this has, I have turns that are wrapped around PVC pipe so that we can easily take those turns and change them from one ratio to another ratio. If I had this one set up as this being the primary side, so 150 on that side, and then this being the secondary side, 300 turns, this would be what kind of transformer? Step up or step down? Step up. And the voltage increase would be by what ratio? It would be a 2-to-1. And again, I can control that stepping up or stepping down based on the size of this turn compared to that one. Now, if I turn it the other way, so that this one is on the left-hand side, that's my primary side, and my secondary side is 150, I do the exact same thing, except now I step it down. Okay? So this is either a step down or a step up based on which way those things go. How many of you guys have a charger that you plug your cell phone into to be able to charge it? Oh my gosh, everyone has that. That's great, because how that works is you guys plug it into a standard wall outlet. If you take 120 volts, try this once. Take 120 volt raw, plug it into your phone and see what it does. Not going to work really well. So the idea behind that is that a cell phone charger is essentially a miniature transformer. It takes 120 volts, which is what I get when I plug something into the wall outlet, and it reduces it down to a 5-volt AC. Now, folks, it's going to be an AC signal because alternating current is what's needed for that. We will use a series of diodes, and some of you, like Ryder, might understand diodes because you study some electricity stuff. What diodes do is they're like check valves for electrical current. They will take an alternating current and force it to be just one direction, so you can make it be direct current with a series of electrical components. Well, what it's doing is it's taking a 120 volt and putting it down to 5 volts for a transformer. That would be a step down transformer. Now that will then supply, in this case, it says that the secondary coil has 30 turns on it, and it supplies 700 milliamps to the battery. We want to calculate the number of turns in the primary, the current in the primary, and the power transform. So I want to do those three with you. Now, I'm going to show you the schematic that we would use for a transformer. A transformer is typically drawn to look like this. This is the symbol that we would use for the transformer.
Should we draw it in the box, or is there something?
Well, the box has the answers to this. I'm going to go through these problems with you, but that's the schematic that you would use for a transformer. The center bar, this right here is the iron core, if you will, laminated core. And then the left-hand side would be the primary, the right-hand side would be the secondary. Now I'm connecting to this 120 volts. So if I have 120 volts AC on the primary side, that's going to transform it into a smaller voltage on the secondary side of 5 volts. They tell us that there's 30 turns over here. So N of the secondary is 30. We want to determine N on the primary. So we want to know how many turns are on that side. And we can do that with that ratio. Right? So for part A, says determine the number of turns in the primary. You guys are familiar with setting up a just a proportion, right? I could say, let's see, I'm looking for n sub p, so I'm going to write it like that. N sub p is to n sub s, as the voltage in the primary is to the, did I do that right? Nope. Yeah, I'm going to do it this way, because I often will get this mixed up. I'm going to say n sub p is to v sub p, as n sub s is to v sub s. Now, you can rearrange that thing that I gave you in any number of ways. We just got to make sure that I have the appropriate ratio set up. Now, I'm looking for the number of turns in the primary, correct? True. So once I get that ratio set up, I can then solve that for n sub p. See how I'm doing it? That ratio would give me how many turns? Say it all out. 720 turns. I hear some mumbling, so I want to make sure that if you're confused on something, that we ask the question. Okay, I want to go back to this because I can see a number of people are like, wait a minute, where'd that equation come from? Could I rearrange this? I know that the equation that I wrote was different than what you see here. Could I rearrange that ratio into 3 or 4 different kinds of things? Could I do that? Yeah. Exactly. So what I did was I chose to write that ratio in a way that made it very convenient for me to solve for the thing I was looking for, n sub p. If you want to go back to that base equation, have at it, but ultimately you're going to take those ratios to determine that value. Are we good? Yeah. Okay, go ahead, Sophia.
We'll have that equation on.
Yeah, so I don't have it up here yet, and the reason for that is that this is new material. I'm going to have to add another column up there, right, to be able to show the equations for Faraday's law. It's not many. The primary, the transformer equation is one of those. Probably Faraday's law would be one of those, right? I think it's important enough for people to understand it, to see it, but it is new. It's sort of like cutting edge, if you will. It's always been something I've wanted to study. We just never got to it. So we're there now. Okay. Now, letter B, the current in the primary. So I want to switch colors here. Switch colors here. We assume for any transformer setup, we assume it's 100% efficient. They're never 100%, but they're close enough that we can make an assumption here to say that we have 100% power transfer. So we're going to say 100% efficiency. So these transformers are designed to really be efficient. When I made this thing, its efficiency is about 8%. I mean, it's very poor. So I'm like, well, I'm not going to have students build something like this because the efficiency is so low. When the people that make transformers and they actually build them to be able to operate, they're operating really efficiently. They do that by submerging them in some sort of dielectric material. They make sure that the cores don't have all these like sharp edges to them. They're usually either an interwoven kind of thing or they're sort of a spherical setup. So this is just inefficient. So if it's 100% efficient, what that means is the power on the input is equal to the power on the output. So electrical power, and I think Malcolm was refreshing his memory on what kinds of things, how we could calculate power. I times V, V squared over R, or I squared times R. So we're going to say that the power is going to be the same on both the input and the output. So let's see, what is the current in the primary? So let's go ahead and write up some equations here. Power would be voltage on the primary multiplied by current on the primary. That would be equal to voltage on the secondary times current on the secondary. I'm looking for the current in the primary. So I just go through and solve that for I sub P. Is it 5 volts AC divided by 120 volts AC, then multiplied by that the current in the secondary, which is 700 milliamps. And when I'm done, I get about 29 milliamps. So we would say that the amount of current in the primary is only 29 milliamps, and that's to provide 700 milliamps at a lower voltage on the secondary side. Okay? I'm going to ask you to calculate the power transformed. So I want to know what is the amount of power being transformed. I want you to try that one. Once you have it, we turn and tell that person, I'm listening for it. Tell that person that you're sitting next to you, what is that power amount of power transformed?
3.5, whatever that was.
So since the powers are the same, right? P input is equal to P output. What did you calculate there? Did you use I of V? Did you do V sub P, I sub P, or V sub S, I sub S? Which one did you do?
I think I did S.
Okay, so you did the voltage on the secondary multiplied by the current on the secondary, which would be 5 volts AC multiplied by, don't tell me to shut down, multiplied by 700, I'm going to say 0.7 amps. And when you go through and do that, you get 3.5 volt amps. It's watts.
Would you have to label that AC or no?
Well, so it's power, and so it's technically not an alternating or a direct. It's electrical power, 3.5 watts. Now, I'll leave it to you to determine that the volt amp is the same as the joule per second. Do you think you could do that? Is the volt ampere the same as a joule per second?
Yes.
Can you confirm it?
Because the coulomb per second.
I mean, I know it should be, but can you do that? Volt amps, that's the same as joules per coulomb multiplied by coulombs per second, right? Volts are joules per coulomb, amperes is coulombs per second. I multiply those together, I got joules per second, that's the one. Okay, good, so 3.5 watts. Let's see if we did it correctly because the answers are hidden there. Yeah, I got it, 720 turns, 29 milliamps, 3.5 watts. I put that up there for me just in case I made a mistake. I wanted to make sure because it's brand new material. All right, last one. I want to see if you can fill in the blanks for me here as far as we can until we get to the actual calculations. So power companies use transformers to minimize what? What do you think you're trying to minimize? Waste is fine? Yeah, they use transformers to minimize energy loss and maximize what? It's not bad, but that's not the term I have up there.
Power, energy, visible.
It's not.
Power.
So the reason why, do you guys remember during the current wars where they're like, no, you don't want to use Westinghouse current because it's lethal. You guys remember that?
They're maximizing current.
They're maximizing safety. So, I know. So when they were like, wait a minute, Westinghouse current is lethal. You guys remember that?
Yeah.
Like, oh, this is going to kill people and da-da-da. It can. If I make that voltage really high, that becomes lethal. So what they do is they use transformers to minimize energy loss but maximize safety. And so how they do that is using this equation. For a given amount of power, if I increase the voltage, if I make the voltage bigger, what does that do to the current?
Oh, I thought the current killed people.
But wait one second. If I make the voltage bigger, it will not increase the current. For a given amount of power.
Power is constant.
So if I make, let's write an equation here. Power is equal to I times V.
Yes.
If I make the voltage bigger, that makes the current smaller. Now, how you can understand the energy loss is I'm going to go back to the equation P is equal to I squared times R. Do you guys remember this is one of our equations for calculating power? Now, I have multiple equations for power. This one shows you that increasing the voltage will decrease the current. This one shows you that I squared R shows power loss in the transmission is reduced by the square of the current. If I can make the current small, I can reduce energy loss in those wires. And it's because that I squared R, would you guys agree the R is the resistance of the transmission wires? And it's non-zero. Especially if the transmission wires span across the country. Now I want to zoom in on that picture for a second so you can see it more closely. We have a power plant. That's where we burn the coal or we run the nuclear power, whatever the case is. But you guys agree we're just boiling water? What we do is we boil water. That steam that comes from that boiling process is then used to turn a turbine. That steam turbine takes a magnetic field and a coil of wire and just rotates them to produce a current. Now, there is a step-up transformer on the outside of that power plant. That step-up transformer is to take the voltage that's being induced from the power plant and stepping it up to really high values. 240,000 volts. One of the quotes from that movie that I loved was when Edison said to his apprentice, you're going to go and sell our thing to the Chicago for the World Fair. They're like, what's the transmission voltage for an AC? What's the voltage for an AC transmission line? He goes, 270,000 volts. Got it. How did they get that voltage so high? Using a transformer. Now you notice that this is not an earthquake. Thank you, I'll be here all week. That's a break in the scale. That's a huge distance from one point to the other. That's done along at 240,000 volts. And the reason for that is I want current here to be incredibly small. Very big V, little I. So I make the voltage really high on those things to make the current small. Now, I step it back down. So one of the keys to safety is that I don't want to have 240,000 volts brought into my homes. So you'll see these things. You don't usually see these. The step-up transformers right by the power plants are not something, unless you live near a power plant, you're not going to see that. But you'll see these little substations. They're all around. They're usually barricaded, right? You got some fences up around them. You're like, what is that thing? It looks like a bunch of electrical components. What it is a step-down transformer. It's taking the 240,000 volts and bringing it down to something smaller. Then we run those little wires that you guys see on the telephone poles that are maybe 100 feet or so off the ground that run along the lines, that are along the roads. Those are at 240 or 2,400 volts. They're not the ones that span across the country. Those things, if you see those way out in the country and you see them way up there, those are really, really high voltages, and that's to make I small. These little bucket transformers, those are the ones that take the voltage down to 240 for your home. Now, what I'd like you guys to do is I would like you to follow along with the mathematics, how you would determine the energy loss in those wires. If I have 120,000 kilowatt or 120 kilowatts, that's 120,000 watts of power, then I want to transmit to a town that's 10 kilometers away. The transmission lines have a total resistance of 0.4 ohms. So there's some energy loss in those wires. Calculate the power loss if the power is transmitted at 240 volts versus 24,000 volts. I'm going to do one, then you guys do the other. So first thing I'm going to do is I'm going to find the current that's needed to develop that much power at that voltage. So for part A, I'm going to say I is P over delta V. That power of 120,000 watts being delivered at 240 volts means that I will have to draw 500 amperes of current through that wire. So I could transmit that power at 240 volts, but I would need a lot of current. Now I want to determine power loss. So I'm going to now change the equation and say P loss. I'm going to go back to this equation that says the amount of energy I lose in that wire per unit time, power loss in that wire, is based on how much current I have flowing through it and how much resistance I have in those wires. Those resistance have only 0.4 ohms, which doesn't seem like a lot, And it's not, but because my current is so high, I've got a lot of loss of energy. So let's go through and do that calculation. I take 500 amps, I square it. I multiply that by 0.4 ohms, and I get 100,000 watts. That represents the power loss, not how much power is being delivered. That represents how much, what's the rate at which I'm losing energy to the wires. Could you do that as a percentage of what I'm trying to supply? I'm trying to supply 120,000 watts, and I'm losing 100,000 watts in the wires. How much am I losing? What percentages am I losing?
Like,
Just do a ratio of 100,000 to 120,000.
you're losing at 83%. Yeah.
This is about an 83% loss. Yeah, they often said in the movie, like they're going to run themselves out of business. They have to put in a power station every mile or whatever the case is. If you're running DC, you cannot transform it at really high voltages. You'd be stuck at putting it out there at 240. Now I want you guys to calculate what would be the power loss in the wires if I transform that voltage to 24,000 volts, so that I can transmit it that 10 kilometers at a much higher voltage. You guys try that one. You guys can do part B, following that example. Is that correct? It's only 5 amperes of current? 500 amps? 5 amps. And I'm squaring that.
0.0083%.
Yeah, I mean, it's a really small value. So that's a key takeaway from that. When I go through and do P loss, I'm taking that I squared R, 5 squared times 0.4. What is that, 10 watts? Is that how much I've lost?
Yeah.
I mean, 100,000 watts, 10 watts. I can live with 10 watts. So what is the percentage? We said 0.00.
0.008.
So as a percentage, 0.0083%.
Yeah.
Okay.
Because it was originally 10 to the negative 5, and you multiply by 100. So.
Wonderful. Mathematics. This allowed us to be able to say, hey, we're going to go ahead and run everything AC as long as we can transmit it at really high voltages. But you're going to kill people.
Yes.
They transform it back down to be able to make it safe to work with. Okay? Well, how much current flows through your body is largely a function of what is the driving force, what's the voltage, and how much resistance do you have, right? So if you touch a power line that's at 24,000 volts, that's a lot of driving force. Even if you have a decently high resistance, you're going to still be hurt, right? So, all right, there you go. Guys, girls, I want you to know that I'm going to stop this video. I want you to know that this is the first time I actually feel like I've been able to get through